in our problem, we're going to use Green's theorem to find the flux of a given region. So Green's theorem says that either of these two methods we could use to find the flux. In this one, we're given our F vector in our problem, and we're also given our region, and we're also bounded by our parametric equation from t is between 0 and 2 pi. In Green's theorem, we can either use the method where we take our m from our F vector and plug it in our n and integrate it that way, or we can take the double integral of our partial of m with respect to x plus our partial of n with respect to y.
Alright, so doing the first method, we know that from the problem, our F vector is negative x squared y I component plus x y squared j component. So going from here, we're going to parameterize it. We know what we're going to say our x value is a cosine t, since it was given our bounds right up here. And the y would be a sine t. So if we take a derivative of each, this becomes negative a sine t. This one becomes a cosine t, and these have dt's after as well. And oops, I forgot the t. Now going from there, since our m is really negative x squared y, this is really, in our mu terms, negative a cosine of t, all of that squared, and a sine t is our y, which we get this to be simply just a squared cosine squared t. And this would actually be a cubed, because the a is going to come over here, so make this a cube sine of t. Cool. And now our n portion is x y squared. So really that's our a cosine t times a sine of t squared, which really is just a cubed cosine of t sine squared t. Okay, now using the first method where up here, plugging into this form, we have our integral, and our bounds of t are from 2 pi to 0 of negative a cubed cosine squared t sine t times a cosine t dt minus a cubed cosine of t sine squared t times negative a sine of t dt. Alright. Now this simplifies, just working with the inside of the integral, to pi 0, simplifies to a to the fourth cosine cube t sine t, oops, dt plus, and split this integral into, not yet, plus a for sine cubed t cosine of t dt. Okay. Now looking at the first part of the integral, since this is addition, we can have these two be integrated separately. You can see that we're going to be using so both these terms have an a4, so we can take that out. This one has a negative sign, so we're going to have negative. Cosine dt sine of t dt plus 2 of sine cubed t cosine t dt. Cool. So now taking the first part, we know we have sine and cosines, and we're doing an integral and timesing, so you're probably going to have to use u substitution to get past this. So we're going to make u equal cosine of t, makes du to be negative sine of t, dt. Now with that, this first part becomes negative integral of u cubed du. Equals, so there's already negative there, we're going to have the negatives take each other out, which this just becomes u to the fourth over 4. We're doing the integral, plugging back what u is, it's cosine of 4t over 4 from 2 pi to 0. Well, cosine of 2 pi is the same as cosine of 0, which is 1, so we're minusing them both, so this just becomes 0. That was just the first part. So the second part here, doing the same u substitution, we're going to say u is actually equal to sine of t, which makes du cosine of t dt. So we have integral of u cubed du and that becomes u to the fourth. And we're going to bring back our u, which was sine of to the fourth of t over 4 from 2 pi to 0. Well, just like cosine, sine is the same thing on 2 pi and 0, which sine of 2 pi is 0 and sine of 0 is 0. So this is also equal to 0. So when you put it back, you're going to get 0 plus 0. Guess what? That is 0. That was using the first method.
Okay, so now we're going to use our second method where we just use our partials, where we integrate it, take our double integral of our partial of n with respect to x plus our partial of n with respect to y. And we said in our problem that n equals negative x squared of y and n equals xy squared. So we take our partial of m with respect to x. That's going to be negative 2xy. And take our partial of n with respect to y. And that will give us 2xy. And then we just plug it into our form where we take our double integral of our region. And you get negative 2xy plus 2xy. And that also will give us 0, just like with Ryan's. It's a lot shorter, but it's also another way you can find the flux using Green's theorem.